Today. Good evening, everyone. Welcome to our seminar series. Today we have Atil Iscen, who is a senior research scientist at robotics team at Google. Prior to joining Google, he has worked at NASA Ames Research Center, and he received his PhD degree from Oregon State University in 2014, and his master and PS degrees from Middle East Technical University. His work lies within the intersection of robotics, reinforcement learning, simulation, and control. And he primarily works on learning locomotion skills for quadruped robots. And today in his talk, he will share with us their efforts on learning-based approaches to locomotion controllers. Thank you, Atil. The stage is yours.
Thanks for the introduction, Aykut. So as Aykut said, I'm mainly working on learning like locomotion, and this talk is about different aspects we have been working on in the last 3-4 years. So it's mainly because of 5 different branches, topics, and they are all different papers published in the last 2-3 years at different conferences. So I will come back to this outline. But mainly why we want to do learning in leg locomotion. So we have seen that traditional locomotion control can already be used, and you have seen probably the robots of Boston Dynamics doing backflips and all kinds of crazy things, and they work. But so they don't use learning in that control. So why do we try to do learning? Mainly the traditional locomotion control requires prior knowledge, and it requires an accurate model of the robot to use manual tuning, and it has a limited generalization. So if you change the robot slightly in that, or if you change the scene slightly, it's much harder to adapt, right? And as opposed to that, if you look at learning-based approaches, there is either no or less prior knowledge requirement, and it's model-free. I mean, we use simulation, there's a model there, but it's not it doesn't need to be an accurate model. And it's semi-automated, so there's still tuning of some hyperparameters, but most of the learning is happening itself, and it's more generalizable. So if things change, we can retrain, and it's much easier to adapt. But what is the challenge with robot learning in locomotion? So deep reinforcement learning doesn't always learn what you expect. It can find all kinds of solutions. We will get to this. But ideally, you would like to have a smooth and safe walking behavior. So that's the first challenge. The second one is when you use training for simulation for training, it doesn't always transfer to real robots because there's a sim to reality gap. And you cannot really train on the real robot because it requires lots of data. Three, you need perception, and the perception is not as a high frequency as controls. So you need to blend the fusion of these sensors or different control stacks. So you need to handle this in training. Next, real-world environments are complex. So in simulation, you see in a bunch of latest papers, there's a really flat terrain. The robot is just doing all kinds of things, but the real world is way different than that. Even the carpet is not uniform. It has a different frictions at different directions. So you need to teach for this. And some tasks are too hard to learn with reinforcement learning without an extra help. So we'll get all these 5 things and how we approach these problems. So these are basically 5 responses or directions to these problems. So first one is learning locomotion using reinforcement learning or evolutionary strategies using trajectory generators. And the second one is how do we handle sim to reality gap and adaptation or learning on the robot. The third one is for mixing vision and controls, hierarchical reinforcement learning. And fourth one is generalizing to uneven terrain. And fifth one is agile locomotion using a monitor. So first, what do we use in this research? as a simulation, we use PyBullet. It's an open source simulator. It has a bunch of robots modeled in there already. Some of the stuff that we already have are already open sourced as well, like the control methods and stuff. So you can find some of these things that I have in the talk in the open source page of this PyBullet. And in terms of robots, so I just gave two examples here. The top one is the Minotaur. It's not built anymore. It was by Ghost Robotics. They stopped building it. They have different robots now. But we were using that a couple of years ago. And the bottom one is Lycago from Unity from China. They actually also have two new robots. They're smaller and more compact and more capable now. But these are mainly what we used in this talk. So for people who's not familiar, what is reinforcement learning? So in reinforcement learning, there's an environment and an agent, and they interact at every time step. So agent takes an action, and it receives a state and a reward. So this loop keeps going, and the goal of the agent is to optimize the cumulative reward that it gets from the environment. So during this training, it changes its policy to get better and better rewards. So first we said, okay, let's learn locomotion with reinforcement learning. So that's the Minotaur robot by Ghost Robotics on top and the simulation. So we set everything up. And normally from reinforcement learning perspective, what you would expect is you set a reward of just walking forward and put the training and it should just learn. And you expect something like this because in nature you see quadrupeds walking nicely like this. Right? So what you get instead is something like this, which is really not ideal. You cannot deploy this to the robot. You will damage the robot. So this is some kind of side effect of reinforcement learning. Because unless you constrain it, unless you penalize these things, it will learn one way or another to achieve the goal. So to go around this, we introduced using trajectory generators. The idea here is locomotion. We know that locomotion is a repetitive and cyclic motion for legs. So we introduce a cyclic generator that's based on time, and it just circles in time. So so let's say if your current state is at some state in the circle, at every time step based on the time spent, real wall clock time spent, it progresses. Right? And then, so we map these state of the cyclic integrator to a position in a trajectory generator. And you set a parameter. So as an example here, we set a parameter of amplitude. So if you change this amplitude parameter at every time step, you can have a trajectory like that. Or you can even have a trajectory like this, and you can have different speeds because that's another parameter, how much you want to progress at every time step. So we eventually build a integrator, cyclic integrator that gives you a trajectory that's customizable at every time step. So what we do is we plug this into the policy. So the policy actually learns the output or input to these cyclic integrator. And the cyclic integrator returns its phase to the policy as an observation. So this is on top of what the policy sees from robot, like state of the robot. And then the cyclic integrator gets the trajectory generator, its state, and that gives the position of the leg. And the policy also adds the residuals on top of it for smaller adjustments. So using this system, we just train the policy again in reinforcement learning, but the rest is fixed. They're just parameterized. And by the end of this training, we were able to get nice walking behaviors. And we deployed on the robot. And one nice, actually there are a couple advantages to this approach. So since we embed prior knowledge, we use a much smaller observation space. We can get away with it. We don't need to know all the leg positions, etc. You can train much smaller number of episodes. You can use a linear policies, much smaller policies. So you basically simplify the whole job of the policy by just embedding prior knowledge about locomotion. And another nice thing is we can control the gait of the robot. So we can couple different legs at different ways. So you can have a walking like this. So the phase difference between legs are a quarter here. Or you can have a bounding gait where the front and back legs are coupled. Or you can have a more like a leaping behavior. So these are all customizable. So you have a control over training. So you can find more details about this at the paper mentioned below, policies modulating trajectory generators. Second topic, it's about sim-to-reality gap and adaptation and learning in the robot. Yes.
Can I have a question? Like,
Yes, sure, yeah.
How does this approach work under perturbations? Like, if I perturb the system, like, does it still stay stabilized? That's one question. Second question is, do I really need like a reinforcement learning in here? I mean, can I, like, what's the main benefit of reinforcement learning for me? Like, can I go with like some other methods like existing? You separated like some learning-based methods versus some traditional methods. I think I can easily get the same results with some traditional methods. Am I wrong?
No, yes, you're right. So you can get this. Well, let me first answer the first question. So on the perturbations, this behavior, that one is pretty robust, but it's not because of some specific property or guarantees. So one thing we train with randomization, so it learns the robust policies. And second, the behavior learned there is by itself very balanced. So it's not like agile behavior. So that's why it works well. But it's also possible to train, add perturbations during training and reinforcement learning. Then you can even have really robust behaviors on much harder problems. So that's one way to get robust behaviors with reinforcement learning. Why reinforcement learning? I mean, it gets to the, I guess, this, if I go back to this slide. So yes, you could get this exactly in traditional locomotion control. But one thing is, if you change the robot slightly, if you change the environment slightly, you have to tune things back. So if you look at, for example, Boston Dynamics, they built that robot for 30 years. They tuned everything. They have really accurate simulation. They have engineers that are expert on that robot. But if you change things, it will take a long time. So in looking at the problem from reinforcement learning perspective, if you give me another robot, it will take me less than a day to get this exact same thing. That's the thing. That's the power of reinforcement learning. It's the ability to adjust, adapt, generalize to different conditions by just changing the robot, changing the reward function, changing the sensors, and etc. So that's why we want to try to get the same things that you do with traditional control so that we can generalize to other things.
I mean, the reason I ask this question because we are trying to use this RL, the human-robot physical interaction, and one of the things I observe is if the dynamics changes, then RL doesn't really perform very well. Like, for example, in your case, maybe if this walking robot walks on some arbitrary train and the dynamics changes continuously, then I don't know how you approach a problem like this. I'm not an expert in RL, but I see like RL is not performing very well because trying to adjust itself continuously, and that doesn't lead to some really robust behavior. Is this kind of making sense? That's why
actually, that's the second section. This might answer your problem. Because it's mainly about yes.
Before we move on, since we are interrupted, I have a really quick question. This looks very similar to dynamic movement primitives, right? You can use like a cyclic basis function. You have your regular trajectory generator in the form of a mass spring damper system, and then you have an added like a learned term. Like it's like, what is the difference?
The difference is we leave here. Well, we don't have as much prior knowledge as DMPs here. So it's just a cyclic trajectory generator that just generates a cyclic motion, and all the parameters are like non-dependent on the robot model. It's just like the amplitude or like the position type things, and these are all controlled by the policy. So you embed much less knowledge about the whole DMP, and they're all like the coupling, etc. All these things are controlled by the policy. So we have much simpler thing as a trajectory generator, and the policy has a much more control over what it can get with it. That's the main difference. It's I would say it's closer to the pure RL. So it's between like the pure RL and the DMPs and combining it.
And actually, two more things. I'm sorry to be interrupted too much, but are you going to talk about your rewards throughout the talk? And do you have any methods to guarantee stability, because you're controlling a dynamic system? Usually in RL, you have to do other things to guarantee stability, and that inevitably leads to either like you learn to fail and then try to stabilize, or you somehow embed model information.
So we don't guarantee this stability here. There are works on that. I don't have it in this talk. They're like using Lyapunov functions. They are trying, and I haven't seen it working that well on Locomotion yet, but people are working on it. I know that, yeah, that's about stability. Well, reward functions, yes. Well, so far it's very simple. The first section was using just forward movement. That was the old reward function. But going forward, it's especially the last section requires more than just walking forward. That's when I will get into more about the reward function there.
Yeah, thanks.
So I will start probably going faster because of the time constraint. But the second section is about sim-to-reality gap. So as from the questions, as you've seen, so when you train on simulation and then you just try it on the robot, it doesn't really work well. I mean, this can be because of the carpet, because of the robot model. So there was this, in this paper, we actually looked at all the problems that might lead to this. So if the potential causes of the reality gap is a model dynamics, wrong simulation parameters like friction, inaccurate contact models like the friction or the contacts, like they say bounciness, the latency within the system, because when you command it in the real robot, it takes some time. It's not like in simulation. Actuator dynamics, they behave differently under different conditions. The noise in the system, the stochastic real environment rather than the simulation's determinism, and the numerical accuracy. So all these things can cause reality gap. When we studied all these things, we found that the two important causes are actuator dynamics and the latency. So if you tune these similar to the real robot, that the transfer is much more smoother, much better. So you can get direct transfer from simulation to real. But that was specific for this study, of course. I mean, for different robots, different environments, it can be different, because if you put it, for example, on a soft surface, then yeah, you need to probably put that into simulation as well. But these were on the flat surface. These were the main two parameters that were important for transfer. Another approach is adapting on the robot. So you train something in simulation, it doesn't work on the robot. Rather than tuning back your simulation and retraining, you try to learn adaptation on the robot with few trials. So this is done by meta learning and meta reinforcement learning specifically. So you basically train a policy that can adapt easily. So that's the whole goal. And on real, you do, let's say, 5 episodes. And then during those episodes or one step in the training, it adapts to that environment. So you change the environment, you just go to another environment, you do 5, 6 different trials, and then it adapts there. So this is another approach. I will not get into details due to time constraints, but let me know if you have questions later. Another approach is on-robot learning. So if you don't want to deal with sim-to-real at all, then you can just train on the robot. Traditionally, it's not that reasonable because it's not efficient. So you need to do hundreds, thousands of experiments on the robot. It's sensitive to the hyperparameters, so you cannot do hyperparameter tuning, latency. The reward signals in real is not always existing as in simulation. The exploration can break the robot. So all these problems, the safety is an obstacle on robot learning. So the solution to this, the way they came up, is using soft actor critic with temperature learning. So you have less hyperparameters, and you also have a much more efficient reinforcement learning. So in this case, they were able to do in 5 minutes this is 5 minutes is another paper later in the top. So after 135 minutes, the robot was able to walk. So they of course have prior knowledge here added. So that's why there's a safety and the robot. You don't break the robot. And yeah, around 135 meters, which is not ideal, but not too bad. The robot can walk. But in these cases, the main goal was just to make the robot walk, right? That problem was already a challenge. But what we eventually want is something like this, because in nature you see the animals doing all kinds of crazy things with the legs. So that's the whole purpose of the legs, right? So how do we get there? So it's more than walking. First, one additional thing needed is vision. So once you add vision to the system, things change a lot because it's a bigger state space from reinforcement learning perspective. You obtain it less frequently. It's more noisy, so it's an exteroceptive observation. So the way we tackle it is we split the control policy in reinforcement learning into the high level and low level. So it's a hierarchical reinforcement learning scheme. I wouldn't skip this fastly, but the main idea here is you have a low frequency policy neural network on the top layer and a high frequency policy at the lower level, so which outputs the robot commands, motor commands. They communicate with this latent command space. So this is you define the dimension. Let's say it's 2-dimensional, and you don't actually know what's past there. It's just 2 floating point numbers. And these 2 layers of the policy learn to communicate between them using that. So the high level is responsible for getting the image information and extracting some useful information from there to the low level, and low level is using that to control the robot. And on top of it, since it's not as frequently as the low level controller, and you also don't need to actually look at the image every time, as we don't do as humans. You don't actually reason about the train every time step, every second. You do it less frequently, so there's this duration part where the high level says, okay, I got this information from the image and the robot state, so and I'm fine for next 200 steps or 2 seconds, and then 2 seconds later it reevaluates it. So this is the way we constructed the policy, and this way we instead of running at every step, the whole high level frequency is running at the variable time steps. It decides when to run. So the policy inference time is much lower. So the training also becomes much faster as a result. And you can handle these less frequent camera images very well. So 3 examples done with this. One thing that I want to show as interesting is on the top, so bottom left, you see these points. So these are the decision points for the high level. So the high level is saying that according to the image, it decides on an output and it keeps it constant for a while. So as you can see, when it's going straight, it's longer. When it's needed, like the corners and stuff, or when it's not sure about the environment, it actually takes the decisions much often. So this is what it learned. Another interesting thing we learned from this is we looked at the latent space. As I said, the high level and low level communicate between them in a latent space, and we don't actually know what is in there, what emerged. So we checked, we set it to 2 dimensions, and then we visualized it. We realized that these 2 dimensions are used for steering at different orient angles and for going longer. So that's automatically emerged from the policy. So that's actually very intuitive to us because that's what we would do. Like when you are walking, you would say, I will go straight for a while and then turn not left now for a shorter time. And it's nice to see that we can interpret these and it's emerged automatically from the system. Then we deployed this to on the more realistic scenes. These are the Gibson terrains. Just to show that it's not only in the, it can also use more realistic sceneries. By this time, we were not able to deploy this trial on the robot due to COVID issues, but we are hopefully now working on it, and we'll probably soon have the real robot doing the exact same things in real environments. Next is the terrain generalization. As you could see, all these terrains so far are flat. I mean, they require steering, but it's still flat terrain. And you could actually use wheels. Like you don't need legs for flat terrain. Right? That beats the whole purpose of having legs. But when you change the terrain to uneven terrain, unstructured terrain, it's a much harder problem because you need leg clearance. You need to have the policy needs to adapt to the terrain, and you cannot just train for all kinds of terrains because in the world there's all like there's stairs, there's like grass, all these things. So what we did is you define the problem as a multitask reinforcement planning. So each task is a different type of terrain, and we mix these things, and we train a policy that can handle all these different tasks. So we switch tasks during training, and we use a curriculum to make it harder and harder. So the environment becomes a distribution rather than a specific, stable, fixed environment. And of course, we need some perception because it's not flat terrain anymore. We implemented 3D LiDAR scans. It's 360 degrees and the 20-degree lateral, vertical scans, and it gives the depth image for all these rays, as you can see on the top left image. So other than that, yeah, the same policy, it's same actions and measurements from the robot. And using multitask, we train. I will skip the equation and the details, but mainly you can see 3 different types of terrains there, and these are different tasks as an examples. And also there are more here. You can see the stairs. There's the uneven terrain on the bottom left, and there are a combination of them on the bottom right. Like there are holes on the ground, there's pillars, there's unevenness at each terrain. So the whole idea is when we train for these tasks, we can generalize to more randomly generated terrain. So this was hopefully, yeah. So it's not looking pretty because I mean, it's of course it's not trained specifically for this terrain, right? But the whole idea is without seeing this terrain, this type of terrain at all, by training a different type of terrain, different tasks, you can actually have a policy that can handle this. Right? So this was the zero-shot generalization work we did. You might see that the robot is not actually taking the optimal path because we don't do actually path or trajectory optimization in the sense that the robot doesn't actually find the optimal path to reach some state. It's just reward, and it doesn't actually perceive the whole path. So it just picks a suboptimal path at the short-term way to tackle it. But the whole goal here is to show that it can generalize to completely randomly generated terrain. Okay.
What makes
yes.
it generalized to the what makes it generalized to this unstructured terrain? Like I still don't understand. I'm sorry.
Okay. Yeah. I know.
My whole point is very simple. Like your dynamics, internal dynamics is changing, and what I observed that whenever the internal dynamics changing, the reinforcement learning doesn't seems to be able to handle situations like this. And here, like in unstructured environment, again, like internal dynamics is changing, right? Am I correct about that? Like it's not like
when you say
walking on a flat surface, like the same dynamics is repeating, kind of cyclic behavior. But here you don't have much like the torques that's going on to the joints and things like that is continuously changing. So how does it really learns in an environment like that?
So
by the way, I don't have a solution. I'm just like trying to understand.
Yeah. No, that's a great question. Actually, that thanks for asking because it will help me making things clearer. So I mean, I squeezed a bunch of things for time constraints, but it's when you have these questions, it's much better to focus on things. So here, for example, the policy is trained. The same policy is trained in all these tasks, right? So although it's not specifically trained for that terrain, the yellow one. So when it's trained for going down the stairs, going up the stairs, or terrains with uneven heights or holes, it actually, so the same policy has to optimize its reward for each one of these or for all of these. So for example, during the training, in one episode, it takes climbing up the stair. And the next episode, it gets going lower on the stair height. So it's one thing, it optimizes this policy to handle all these four, in this specific example, these four terrains. Right? It generalizes, it kind of, when you do optimization, it extrapolates, right? So because there are similarities between these tasks and the terrain. So due to those similarities, it can perform at that terrain. It's same with when you add. Actually, another thing we need to consider is the robot isn't blind, right? It has the LiDAR sensor, so it has an idea of the terrain. So it's not actually, since it's not acting blindly, it doesn't act as if it's acting on a flat terrain because it sees that there's a small bump or small hole in front of it. So it takes a different action due to that perception. So so it's not doing the exact same thing as it was in the flat terrain, or like if it's climbing the stair, it sees that there's a stair up. It learned to do specific actions for it, like lifting legs more, let's say. If it's going down, it learned to go like changes body orientation to the front lower. And to training to be successful, it needs to succeed at all these tests. Right? So otherwise we say training has failed. And then we take it and then try it on the different tasks. So there are more actually on the multitask reinforcement learning context. There's a lot of non-locomotion studies on it. So you can train a reinforcement learning policy to succeed at non-training tasks. That's the whole research area that people are working on. We are just using one small part of it here. Does that help, or you have?
It does. Like I was wondering, like how many such kind of scenarios that you have to feed to be able to cover arbitrary, because I can quickly ask, like for example, if the legs on the left side versus right side are walking on an uneven terrain, like right side, let's say a bit higher, left side is kind of lower. Can it, for example, handle something like that?
Yeah, that's a good question. So in this case, yes, it can, because we have 4 types of terrain here. Mainly, actually in the paper, I think it's 5. There's the rugged terrain, the bottom left, the stairs up, stairs down. There are holes on the terrain, and there's the pillars, like the columns. So these 5 types of terrain, but they are not fixed terrains, so they are all parameterized. So for example, for stairs, there's the stair height and there's stair length. Those are 2 parameters of the stairs terrain. The rugged terrain, it's generated by some random noise, but there's still the mean height difference. So these are the parameters. So there's actually unlimited amount of terrains that we train on, but it's only 5 types. So that's what we use as 5 tasks. But when we train like 2 million episodes on this with all these parameters, I'm almost sure that it has seen terrains where the left feet are higher than right feet, because it will be generated at some point, because so they're all based on some parameters, but they're all randomly generated every episode.
Thank you.
We just define the types.
Yeah. Thank you.
Okay. Yeah. Is there any other question about these uneven terrains? Otherwise, I will just switch to the last section. That's more about the harder tasks and using like in the midst of reinforcement learning and the rewards. Okay, and we can always go back to these other sections if you have questions. So the problem, so you have seen so far walking and more like careful walking behaviors, but the goal we had in start is achieving agile locomotion behaviors, such as the one you see here. But it's a very hard problem. First, it depends heavily on the context. It's a high-speed action. You need to carefully plan the whole thing, because as you can see, even in nature, the animals can make mistakes about it. So if you underestimate the friction or underestimate the length you can jump, with small errors, you end up just hitting your head. So we want to learn this behavior, this kind of behavior, and succeed at it. And we want to use the same things we have already, the reinforcement learning, right? The way we approach the problem is mainly if you set the same reward function, which is, let's say, going forward, it will never learn this. First, it's a very hard problem. There's a very high local maxima where you just learn to walk and then fall at the gap. And unless you succeed at going the other side of the gap, it will never learn to achieve the test. And we need to somehow help this with, let's say, reward functions or some kind of prior knowledge we have. Otherwise, it will not learn. In the traditional controls, you first plan the trajectory, and you will find the center of mass trajectory and how it will jump, and you try to satisfy that trajectory. In reinforcement learning, so far we have not been doing that. So how do we tackle this problem? Is the problem here? So the training method we split into 3 stages. We first simplify the problem, and we find the best mentor. So we define a mentor to the robot. So on top of what it will learn how to achieve the task, there's another agent that will help the robot learn achieving the task. So it's a kind of a multi-agent training, but when there's a mentor helping the agent and the agent is learning the task, and there's the environment, the internet. After we achieve this task, the first one, the simpler one with the mentor, we re-diversify the environment, make it more complex again, and then we try to have the agent or robot adapt to this. And then at stage 3, we want to remove the mentor from the system. So imagine this mentor as a when you're learning to cycle, many of us had these extra wheels at the back of the bicycle, right? The mini small ones for helping with the balance. But at some point, once you are comfortable with cycling, you remove them. And actually, at some point, you first get them higher and higher. So you learn to not rely on them, and then you remove them eventually. Okay? So this is what we try to do here. We first introduce the mentor, learn the problem, and then remove it. So this is the whole 3 stage we have. So going into more details, in stage 1, how do we define the mentor? So this is the traditional reinforcement learning figure where the robot gets observations, it takes actions. So the way we introduce the mentor to the system is by accessing the ground truth from the environment and providing extra observations and the shaped reward. So first, the robot doesn't have access to all the information. So the observations gives us partial observation most of the time. So let's say it says a LiDAR, but it doesn't know exactly where everything is. So mentor has access to this. So we kind of cheat, and it provides these extra observations and changes the reward. So in this case, what's the mentor? How do we do it? We put this coin or sphere that the robot learns to get there, and the reward is at every time step, it gives a reward for getting closer to there, and it gives a bonus for reaching the position. And then once it reaches, it disappears. So we have one large reward for reaching there, and many smaller rewards, denser rewards for getting closer. So this makes the problem easier to learn because you get both long-term reward and short-term reward. And we shape the test. So the observation-wise, it actually gives its relative position to the robot at every time step. And it says, I'm 3 meters up, 2 meters in front of you at every time step. So this is also rely on the ground truth. And then this helps the robot learn as well because it learns precisely how it gets closer to the goal. It makes it easier to achieve. And the next question is, of course, how do you define this sphere, right? Where do you place it? How big it is? How do you know this is the best one? We don't, but we define it as 5 parameters to define its location and size, and we optimize them as a hyperparameter. So as an example, we can place it further away from the gap. We can put it closer to the cliff, or it can be very small in the top right, or it can be very large. So these are all potential ways, mentors, and we just find the best one by doing hyperparameter optimization on top of learning. The controller details, we use the PMTG, that was the first section we had in this talk. Observation-wise, we have IMU, the motor position encoders, and the LiDAR, that's 20 by 20. And as an action, we output the motor positions, 3 per leg, 12 total, and we do position control at 100 Hertz, and they're converted to torques using a PD controller. To give idea about the LiDAR sensor, how it works is, so we have all these rays, and when I freeze the frame on the left, it's actually what it sees is on the right. It's a grayscale image based on distance. You can see the gap in the middle is black, but it sees the terrains. So this is part of its observation. So in some sense, it's actually doing vision. The LiDAR acts as a depth image, but it's just centered and defined it using these 20 by 20 rays. So we feed this to the policy. In stage 1, so the robot learns to walk first and then runs. It slightly gets to the other side, but we need to think that here the environment is fixed. We don't change anything because it's a much simpler environment. Otherwise, it never learns. And then the mentor is also fixed. So the whole goal of this first stage is just learning, being able to do one specific example, right? And here we optimize this as a hyperparameter, these mentors. So we find what is the best kind of mentor, where should we place this, and where should we, how large it should be. Right? So once we achieve this, we pick the best agent and best mentor. We move to stage 2. Here, I just give an example of randomizing the gap position, but you can randomize many more things, right? The friction, you can randomize gap length. So we start randomizing these things and keep training. So first, the performance drops, of course, because the robot is not used to doing different tasks, but then it adapts. But there's still the mentor, actually, where it's placed based on the gap location. So mentor helps the agent adapting to this. In stage 3, we remove these training wheels, right? We remove the mentor, and we use sensor dropout. So we probabilistically remove this the mentor, and we use a curriculum where we have it all the time to where we remove it all the time. So it gradually increases this probability of removing it. And by the end of the training, the robot can do things like these. So these are the emerged behaviors. It looks very natural, and we can see that the robot adapts to changing its stance to jumping before, and it actually learns to land and change its feet to stop the connect, not have contact with these things. So this is by the end of all 3 stages of training, and this doesn't use the mentor at this point. So yeah, we achieved these, and then now we are trying to deploy this on the robot. But yeah, as I had these questions, yeah, there's a simulation to reality gap, and it's much larger in these behaviors because the robot is relying on fast action, the friction, all these things. So it's much harder to transfer this to the real robot. That's what we are working on right now. So this was the outline. We can come back if there are any questions. But yeah, the first part was learning locomotion using trajectory generators. Second part was the sim-to-reality gap, adaptation and learning on the robot. Third part is hierarchical reinforcement learning to handle the vision. Fourth part was generalizing to uneven terrain. And fifth was this agile locomotion using a mentor. Yeah, thanks for listening and inviting me. This was the end of it. If you have any questions, I think we have around 7 more minutes. And I have more time after that as well, if you have questions.
Thank you, Atil. Yeah, we are open to questions.
I mean, I have a few, but since I already asked, I can let especially students ask questions if they have any.
So maybe I can ask a question about the first work, about this cyclic integrator.
Yes.
So are those handcrafted or designed, or that's a part of the training stage? Because nowadays we have these neural ordinary differential equations. So when I see the cyclic integrator, I just think whether we can just inject those components just to make this part of the training.
Yeah, that's that's a good direction actually. I didn't so we didn't optimize it well, mainly because we didn't have to. So in this work we only defined as a circle, right? And we only have one parameter, that's the amplitude, and the second parameter is the speed. And it can generate it can generate a bunch of different things with that. Just with these two parameters, it's like something like this. It's easy to generate. So once we had these, we didn't need to handcraft further, and it already learned to do it. But there are a few things that one is how much freedom you give to the trajectory generator. For example, you can set the boundaries for this amplitude. Right? If you set it too small, it will only be around a small circle area. It has the freedom it can generate. If you provide much, it can generate all kinds of things, but then you go back to the original problem. Reinforcement learning will learn all these kinds of weird behaviors. How do you balance that? So we just defined those boundaries. But other than that, yeah, we didn't really optimize it in this work. Later, last year, we defined it using a spline with 3 points, because normally when you walk, you have 3 different points where you have the peak of lifting your leg, foot, and then putting it down, contact start and the contact end. So we switched using splines, used these 3 points, and we could optimize it a lot, but we said, okay, as the policy can select these parameters, let's just define the boundaries and give that freedom to the policy. But yes, I'm guessing it will be possible to get better results if this is also optimized. But kind of in locomotion and robotics, you kind of have would have the human in the loop. That's one aspect of it. You cannot automate everything, because although the policy optimizes things, when you look at it visually, it doesn't look nice or it doesn't look feasible. But it's hard to define these things in the optimization process. So that's why I personally think having the machine learning automate many things and having a human in the loop still is the best of both worlds. But yes, I agree that if you could optimize it, maybe the policy will find solutions better than we think. Right? Maybe a spline with 3 points is not the best. Spline with 5 points is better. Right? All these things are possible.
Thank you. Thank you.
Yeah.
Can I ask you a question?
Yeah, sure.
So thank you for the talk. I was just going to ask, before your zero-shot classification, no, zero-shot experiment, in that model, are you using the cyclic integration that you did in your first study?
Yes, yes, yeah, all these use that.
Okay. Did you try to use like a model without cyclic integration? Because I would think that would hurt the model somehow, because when you are like in the third, like bottom left example here, the terrain is changing always, and if your robot is doing things like the same thing all the time, then it would fail, I guess. No?
Yes, that's a great question. It would fail, but the main thing is with that trajectory generator, the parameters of the trajectory generator are set by the policy at every time step. So if I go back to this, so these parameters, the trajectory generator's parameters are set every time step by the policy. So this means that if it sees there's a, let's say, there's a bump in front of it, it can set the lifting the foot to be higher at that time step. And few time steps later, if it's flat, it will set it to lower. So it doesn't need to use the same trajectory. It actually generates a trajectory at every time step.
Does it carry over time steps? The parameters
yes.
like carry over?
Yeah. So we actually had an experiment in the first paper where we give command to run at specific speed, right? And when we command to go at higher speed, it actually learns to have larger strides, or it learns to move the legs much faster. When you lower it, it actually lowers those parameters. So it's the same with the terrains. If it's a flat terrain, it learns to, since it's stable, it learns to do larger strides. Or if it's rugged terrain, it learns to lift the foot much more.
Let's see. Thank you for your answer.
Yeah. I can go on. First question about the last study. Very interesting. It's a very clever way of doing reward shaping. But even in the videos, we can see that like the joints separate. Basically, I mean that's the problem with simulation. Basically, when you have penalty-based contact enforcement, right? Do you think can such a simulator be useful to sim to real transfer ever? Like I mean, we've actually we made these stable relatively recently, at least for open source projects, like 5-6 years. I mean, relatively recently in terms of the technology. We had simulators for a long time, but back in the day, like things would explode with these like penalty-based contacts. Do you think we need to make improvements in contact simulation and perhaps like merging more realistic simulation, like not contact-based penalties, but perhaps I forgot the term for it, but we have better ways of doing like this forward dynamics for articulated bodies. Do you think we need those, or do you think we can do it with the existing simulators?
Yeah. So first, I should clarify about that joint breaking because the author of PyBullet is actually in our team and he's pissed off at me already because I have that video there. So normally those joints are not like that because we meshed the robot to look nicer and cleaner. So we just put an overlay, and then the actual joints are not that looking that way, and but it's just the visually to make the video nicer. We had that problem. We didn't pay attention. So the simulation-wise, it's actually robot-wise, it's very accurate. As you actually had a really good point, the contact is the main problem in simulations. But this can be used very well on sim-to-real because I don't have the videos in this talk and I cannot show them right now. But we actually had a bunch of things working on the real robot, and they were actually looking very close to real. So we know that the simulation is very realistic, and it actually transfers. And if you look at other works like ETH, Zurich Animal Robot, or Oregon State has the Cassie robot biped. They all succeeded in the last 2 or 3 years to do sim to real transfer without any extra things. And biped is even harder problem actually, and they succeeded at it by just using similar simulators, by just randomizing things and more robust controller. That's definitely possible. But having said that, if none of these work actually show very agile behaviors like running, jumping, sliding on the tech, heavily friction dependent behaviors, those might have problem with sim-to-real. And we don't know yet. We are just barely scratching that surface. So I don't know if any of these, like if, for example, this one, we are just testing it. We don't know if the robot can actually do approach it and slide it. Like, for example, here it slides if you look at the back legs. Is it going to act that way? We don't know. Is it going to transfer? Yeah, we don't know that well. And I'm skeptical, but you can always improve the simulation. But yeah, it's a trade-off, definitely, because there are terrains we still don't know how to simulate, like in grass. Right? But yeah, so far for non-heavily agile behaviors, it's actually the current simulators are good enough, I think.
Second question is it's a bit more philosophical perhaps. We've actually had reinforcement learning based workers for 25 years now, right? And there's a gap in the literature, like there's a big gap, but of course not biped, of course not, but like spider robots, we can see examples from 1990s, quadruped motion from early 2000s, all doing reinforcement learning. Other than this agile behavior, like what changed? Like they did similar things, and I guess some of those were frowned upon, like exactly using splines to describe robot motion. And then it feels like we came full circle back to these, some of the methods. Like what happened in between? Like, because I'm sure you're more, you're an expert in the related work than we are. So I just want to know your take. It's not like a question, but like whatever, take of an expert in the field.
No, that's a very good question, because we actually joke with our team all the time about we are circling back. We are keep using that. Like we look at we just watched Michael Reibert's videos from 1980s, where the whole spot robots behaviors, Atlas behaviors are based on right now after 30 years, 40 years. But even for them to go from that to like Atlas doing backflip, it took 30, 40 years. And reinforcement learning, if you look at the reinforcement learning cycle, yes, the reinforcement learning has been around for a while, but in robotics, I would say it is maybe has a history of 10 years or so, because it used to be very simple, the reinforcement learning. It couldn't handle the state estimation, the neural networks were not used. So right now we can embed the images, all these things. So we looked back, but we got a lot of things on the way while looking, especially from vision folks, from these simulations got much better, much faster. So we can, even when I was a grad student, training was taking 4 or 5 days. Right now it takes a couple hours. So all these things, yes, but we still use primitives from those areas. But yeah, we got a lot of different things. Like reinforcement learning got better too. Yeah, I think that's.
No, I think like the answer is having a larger, at least raw state space, like embedding images and larger sensors. I agree. Yeah, and perhaps one last question. For these, are you doing more black box RL methods or more like white box stuff?
We use mostly black box, but in some of these works, out of these 5 sections, the first one was done with the PPO, RL, and then also evolutionary strategies, augmented random search, which is complete black box, and it's not even RL. But so we use those, and then the rest is mixed. But there's we never use white box type RL in these.
Yeah,
so yeah, they're more agnostic. Yes.
Yeah. I mean, I feel like for robot stuff, I feel like black box works better in general for some reason.
In simulation, yes. In real, we don't know.
Yeah. I mean, I don't know. We've tried some stuff in real, but
yeah. So, for example, to give an example, there are now differentiable simulators, and with differentiable simulators, they are trying to train on the robot, and it takes much faster. Right? After I would say 10 trials, you can have the robot learn, because the whole thing is differentiable. It just propagates all gradients. So those learn much faster. But do we need them? I don't know. We don't know yet.
Thanks. Very good talk. Very informative.
Thank you. Thanks.
Çağatay hocam.
Yeah, I mean, thank you. I could guess it, I guess. Atil, actually, I like to think that was very nice talk, especially it was focused on RL. And we currently working on this physical human-robot interaction. And I brought this dynamics issue quite a bit because like as the human dynamic, I mean, like, as the robot's dynamics changes, human also adjusts its dynamics to the robot, especially in physical interaction. And that makes the things harder. And if possible, I like to meet you, you know, privately and I mean, like tell you more about our problem and maybe pick up your brain about possible solutions because we have a hard time. I hope that you're available and we can meet maybe over the Zoom meeting.
Yes, definitely. Actually, I forgot to mention, yeah, we are, our team is very open, although it's Google, we are very open to external collaborations. We actually have a couple already. And outside of official collaborations, I'm also happy to have chat. And yeah, I mean, as you said, the problem is hard and interesting. So I would be very happy to have a discussion over it.
Yeah, it's a coupled dynamics problem, human dynamics and robot dynamics. And that's whenever you have this coupled dynamics, I guess like we observe that reinforcement doesn't work very well, but you know, you have so many and we can try it out. We are not experts in the RL.
Yeah, it's an interesting problem, definitely. Yeah.
Thank you. I'll contact you privately, okay, if you don't mind.
Yeah, sure. Yeah.
I have one last question. So basically, you showed that so these behaviors learned with reinforcement learning, they don't look that much natural. Like in computer vision, for some time we are using this adversarial training strategy, like use them as a kind of extra regularizer. So are there something similar in the robotics domain? Like, for example, we can detect joints like in computer vision sense, like skeleton of these different behaviors. And on one side, we have these natural movements by the animals and then apply this adversarial strategy to make them look more.
That's so adversarial strategy is actually lately in the last 3-4 years used a lot in training in robot locomotion. But the way they mainly used is by changing the environment. So it's actually very similar to the previous question. So the adversarial agent is trying to break the robot's behavior by changing the environment parameters, let's say friction, or generating the terrain. Like you start with the flat terrain, right? The robot learns to walk, and once it learns to walk on flat terrain, the adversarial changes the terrain to make it not be able to walk, and then they actually it's used for training very robust behaviors. That's one way to use it, and it succeeds, but it's hard to tune because otherwise locomotion is already a hard problem that it's very easy to break. So, but it's not easy to learn. But other than that, there's also another line of research that where they actually learn world models from pixels for locomotion. This is done in simulation in Mujoko actually, but so the robot there's instead of using the robot's sensors, they have a camera looking at the way we see it right now, and they train a world model on it, and then it predicts the future based on that from pixels, like a video kind of thing, and then based on that, the robot learns to act on that video or in that latent space, latent world, based on purely on the camera images, and they succeeded doing all kinds of things with it, and they also used adversarial on that to make it first to make it robust, and also to make it maybe transfer to the real world, because now the transfer is much harder because you are now looking at the camera image rather than sensor information on it, right? But they have been pushing that line of work, and it's very interesting actually.
Thank you. Are there any other questions? Or I think that's it. Again, thank you, Atil, for this really interesting talk. And it was good to see you.
Good to see you too. And thanks for inviting. And thanks for all the interesting questions as well.
Görüşmek
üzere. Teşekkürler.
Atil, teşekkürler tekrardan.
Teşekkür ederiz. Görüşürüz.
Ben teşekkür ederim. Çok memnun oldum. Görüşürüz.